Hello everyone. So we talked quite a lot about how to find the signed area between a curve and the x-axis, or how to find the area between two curves, but there's always curves that were represented y in terms of x. So what should we do where x is in terms of y? Well, basically we do the same thing, except in everything that we do, the y and the x are swapped around. So we'll have curves x in terms of y, and instead of integrating with respect to x, we'll integrate with respect to y. And instead of finding the area bounded by the curve on the x-axis, it will be the curve on the y-axis and so on. So basically, we just swap the x and y's everywhere. So let's see how that works. So some regions are easier to understand by thinking of x as a function of y. That's why we're going to do this. So, okay, the signed area of the region between the y-axis and the curve x equals f of y from y equals c to y equal d is now the integral from c to d of f of y dy. So it's basically the same as before. The only changes were now we're finding the area bounded by the curve on the y-axis. And instead of y equals f of x, we have x as a function of y. And instead of x equals 1 and x equals 2 for our limits, we have y equals c and y equals d. And then we're integrating our function with respect to y. Okay, and similarly for area bounded between two curves. So if we have two curves, x equals g of y and x equals f of y, and we must find the area bounded from y equals c to y equal d, then we integrate from c to d the absolute value of f of y minus g of y. So this is the same formula as we had before, but before we had the area bounded by two curves which were functions of x, and we integrated the absolute value of f minus g. So everything is the same, just the x and y's are swapped around. And by the way, how would we actually do this? So remember back into the case when y was in terms of x, we could integrate this absolute value by splitting up into different separate regions. In each region, there was one top curve and one bottom curve, and then we integrated the top curve minus the bottom curve. And in this case, we're going to do something pretty much the same. We're going to split into a bunch of regions, and in each case, integrate the right curve minus the left curve. Okay, so let's do two examples that demonstrate how this works. So for instance, let's think of the curve x equals y squared and find the area between the curve x equals y squared and the y-axis from y equal 1 to y equal 2. So the curve looks a little bit like this. So notice that this curve is easier to understand when x is a function of y because there is a piece above the axis and a piece below the x-axis. If we try to write this curve as y in terms of x, we would have to take two functions, right? We would have y equals plus square root x for the top, and then we would have y equals minus square root x for the bottom. So instead of thinking of two functions of x, we could just think of x as one function of y, which makes things simpler. Okay, so let's see how it works. So all we have to do is it's an area bounded by the curve and the y-axis. It's on the right side of the y-axis, so that's the positive area. The negative areas are the ones on the left side of the y-axis. And all we have to do is integrate from y equal 1 to y equal 2. And notice that in this case, our limits are going to be horizontal lines. The boundaries are horizontal lines, unlike with the other case where the limits were those vertical lines, x equals a and x equals b. So we just have to integrate y squared from 1 to 2. Okay, so we integrate y squared, we get y cubed over 3. We plug in our endpoints 2 and 1, we subtract, we get 7 over 3. So this is a pretty standard example. How about the area between two curves? So let's try to find the area enclosed by y equals x minus 1 and y squared equals 2x plus 6. So as on the previous page, y squared equals 2x plus 6 is going to be way easier to think of where x is a function of y because we can just solve x as one function of y. If we try to think of this as a function of x, then we would have to solve, we would get y equals plus square root of 2x plus 6, y equals minus square root of 2x plus 6, and then we would have basically three curves floating around, which would be a huge mess to think about. So let's rewrite these as one function of y and another function of y. So the second curve can be represented just as, if we rearrange 2x equals y squared minus 6, x is a half y squared minus 3. Okay, and now we are supposed to find where they intersect. So since we were not specified limits, we have to find limits by finding intersection points. So these curves are going to intersect when y plus 1 equals a half y squared minus 3, so when the curves agree. So we can solve this quadratic equation, rearrange and factorize, which I'll skip over. That's going to give y equals minus 2 and y equals 4. So these are our limits for the integration. And now we have to figure out which curve is on the right and which curve is on the left. So for instance, we can plug in a point in the middle. So if we plug in, say, y equals 0, for x equals y plus 1, we would get x equals 1. And for x equals a half y squared minus 3, we would get minus 3. So the x equals y plus 1 is going to be on the right in this region because it has a bigger x value. Okay, so the right curve is y plus 1, and the left curve is x equals a half y squared minus 3. So here is a picture. So we can see the region. So on the right, we have x is y plus 1. On the left, we have x is a half y squared minus 3. It has a shape that looks a little bit like this. So notice, for instance, that it's like y equals x squared, but the x and the y's are swapped around, so they orientate, so it's kind of rotated. And then we just move it back by 3 and just squash it a little by the half. So thinking about curves x in terms of y, you can basically just think what would it look like if y was a function of x, and then you have to swap the x's and y's. So you have to rotate the picture. Okay, so here's our nice area. It starts with y equals -2, and we're integrating up to y equals 4. We integrate the right curve minus the left curve. Okay, so here we have right curve minus left curve from -2 to 4. We do our integral, we expand the parentheses. We make sure that we take care to distribute the minus sign. So we're going to get -12y² plus 3 plus 1 gives us a plus 4, and then we have the y. Now we integrate with respect to y, so that's just like integrating with respect to x. It's the same rules as long as we're integrating a function of y with respect to y. So we find our antiderivative, we plug in the endpoints, and we subtract them. In the end, we will get 18 for our answer. Okay, so just to summarize, so we can think of curves also as x in terms of y. Sometimes that's useful because if we have squares or things in, we don't want to have to take square roots. That will give us 2 curves instead. So sometimes we think of x in terms of y. Then to find the signed area bounded by the curve on the y-axis, not the x-axis, but the y-axis, we integrate with respect to y. And to find the area bounded by 2 curves, we have to integrate the right curve minus the left curve. Okay, thanks everyone. See you next time.